mechanism of the gas permeability to the carbon molecular acidity membrane. Jacob E. Parrish, Abraham Stoffer, Chemistry Division, Nuclear Research Center. We have
I would like to present here the molecular sieve carbon membrane and to talk a little bit about the mechanism of gas permeation through the narrow pores of the carbon membrane. In contradistinction to polymeric membrane, where the permeation is through a dissolution mechanism, with the carbon membrane, the mechanism is what we call the molecular sieving effect. And in the first slide, you can see our membrane, which is in her hollow fiber configuration. The diameter is 120 micron and the wall thickness is 6 micron. So you can see that it's a real membrane in a sense that it's not a compact powder, but it's a flawless, without pinhole membrane. We can get membrane that is impervious to all gases, so we are sure that there is no pinholes in it. So we can gradually open the pore structure and receive the molecular sieving effect for many pairs of gases. Here's a schematic scheme of the measurement system. We have here we have the one hollow fiber which is potted here, so we can disconnect the inside and the outer side of the hollow fiber, and with a differential pressure transducer, a very sensitive one, we can measure the permeability. Here I will present some of the results. I'm sorry for some mistakes here. The pressure axis should be -3, so it's thousandths of torr, this axis. And here it's the permeability. Here it's in bar, but it should be hundreds of bar because the usual unit differ from the bar unit with 100, and those are the usual units. So it's hundreds of bar, and this is thousands of torr. And we can see that as a function of pressure, the permeability of argon, helium, oxygen, and hydrogen, there is no much dependency on pressure. Those gases, the measurements were taken at room temperature and higher. For those gases, it's at room temperature. For other gases that we know that is adsorbing, we can see that the permeability is decreasing because of the adsorption or the pore entrances. N2O, carbon dioxide, and methane. As we increase the temperature, we can see, this is for methane, that the decrease in the permeability is slowed down. And another example for carbon dioxide, we can see that the decrease in the permeability with pressure is slowing down as we increase the temperature. I'll try to explain all those results. If we compare the fluxes, we can see in the first equation, that's the permeability by definition. This is the permeability, that's the flux that permeates, and that's the pressure gradient across the membrane. And if we compare that with the first fixed law, we can get that the permeability is the diffusion coefficient times dc to dp. If we assume that the diffusion coefficient is at room temperature and above, is not, we can disregard the dependency on concentration of the diffusion coefficient. We see that the permeability should behave as the slope of the isotherms. And since we are talking about molecular sieve carbon, I'll show later adsorption data, we have a type 1 or Lange-like isotherms, and the slope of the isotherm is decreasing as we increase the pressure. So with the molecule that absorb carbon dioxide and methane, as I've shown before, there is a decrease in the permeability as we increase the pressure. And if we increase the temperature, I've shown that that decrease was slowed down. And the reason for that is that as we increase the temperature, we all know this is the isotherm. As we increase the temperature, the slope of the isotherm decreases. So, for each isotherm, there is a decrease in the slope, but as we increase the temperature, the slope, the permeability decrease slows down even more. And with the permanent gases, that I've shown that there is no dependency on pressure, is because that with the permanent gases, the absorption is in the Henry Law's region, and in the Henry Law region, the slope is constant. So we receive no dependency on pressure for the permanent gases. Here I want to show some adsorption data on the carbon membrane material. And you can see that we begin with a membrane that is almost impervious to all gases. The gases here, carbon dioxide, hydrogen, nitrogen, xenon, and SF6, this is the sequence that we can gradually open the pore structure. And we can show that as we open the pore structure here, slow adsorption of carbon dioxide begins, very slow adsorption of hydrogen, no adsorption of nitrogen. Here, when it really adsorbs, I just gave the amount adsorbed at the plateau of the isotherm. Here, nitrogen is slow adsorption of nitrogen. And as we open it, we can see the nitrogen start to adsorb, and there is a full isotherm here, but xenon is hardly adsorbing. And to show the difference, I gave kinetic measurements. So with M16 membrane, it's the most open one, give much more than 106 micromole per minute. And later on, we started to close the membrane again, and you can see that here, xenon is not absorbing at all, nitrogen is slowly absorbing, and we can reach a point that only carbon dioxide is absorbing. That's adsorption data on the carbon material. So we have a real molecular sieve material carbon material. Here, I have returned to permeability measurements, and I want to show the same results as we've got with the adsorption data. We changed the pore dimension. We increased gradually the pore dimension of the membrane, that's permeability measurements, and we can see the same results that we received before. And we measure the permeability at different temperature. At room temperature, we can see that we can increase the permeability and then decrease it. The same way that we received with the adsorption data, with the carbon material itself. And the same behavior happens at 200 degrees and at 300 degrees. And as a matter of fact, we can go higher up to 800 degrees centigrade or 900 degrees centigrade because it's carbon. And in the next slide, I just put it on a graph, hydrogen and methane. This one is hydrogen. We can increase the permeability and then decrease it. And with methane, which is a bigger molecule, that the graph is shifted. This is for, I'm sorry, this is for hydrogen and this is for methane. Of course, at that point, with that carbon, we can receive huge selectivity between methane, which is not penetrating, and hydrogen, which is penetrating. Just a few words about permeability and selectivity that we received with the carbon membrane as compared to the polymeric membrane. We received up to 3 order of magnitude higher permeability than any polymeric membrane. But there is a big but here. We have homogeneous, what we call symmetrical membrane, which is 6 micron wall thickness, and the best membranes on the market are asymmetric membranes, which have the dense layer. The asymmetric layer has 1,000 angstrom. So even so, if we normalize to the width of the membrane, for some molecules we are better in 1 order of magnitude. For some molecules we are the same. Selectivity, we can reach higher selectivity, depends on the molecule, because the mechanism is completely different. For instance, for hydrogen methane, you can receive absolute infinite selectivity because methane is not penetrating. With polymer, methane is dissoluting, so one cannot receive absolute or infinite selectivity. Another thing that I want to show, what happened with mixtures. Because if we are talking about molecular sieving effect, if we have, for instance, methane and hydrogen, one would think of that the huge methane would block the pore, or the hydrogen would permeate after the methane, so we want to see the high permeability of the hydrogen. It would be a fouling effect. But that's not the case. Here you can see we have a hydrogen-methane mixture. Here it's at 500 degrees centigrade. Of course, with polymeric membrane we cannot go higher than 200 degrees at the most. And you can see that different mixture composition, and there is no difference between the experimental figure and the calculated one. And the calculated one is, here is the equation, the partial pressure of hydrogen times the corresponding molar fraction of hydrogen plus the relevant for methane. So there is no fouling of the methane. The reason for that is our model. I don't have time to explain it, but it's a series of constrictions in parallel that could explain why methane is not fouling the hydrogen. And here is another data of mixtures. I on purpose picked a membrane that don't give high selectivity, so methane would permeate a little bit. Otherwise, one would think of that methane is completely excluding, so it doesn't interfere. So I took an open membrane that methane do permeate, and there is no influence on the permeation of the hydrogen. And I even go down to -45, and -45 methane is adsorbing, even at -80, and methane is adsorbing, and there is no influence on the permeation of hydrogen. So it looks as if it's a good membrane for commercialization.